In this video, we're going to look at one-way ANOVAs, which will allow us to conduct difference of means tests for multiple groups. That is, if we had a continuous dependent variable, let's say income, and we had individuals broken down by ethnicity, let's say into groups for whites, blacks, Hispanics, and other, we may ask whether or not the income levels on average are different for those different ethnic groups. We can once again do this in what is called a one-way ANOVA table, which allows us to compare whether the variation within groups is different than the variation between groups. That is, the fundamental question is there more variation within each ethnic group than there is between the groups in terms of income levels? If there's more variation within the groups, then we would be able to say, with some degree of confidence, that the mean levels are not different. If there's more variation between the groups in their mean level of income than there is within groups, we would say that there is a relationship between ethnicity and income. Once again, this sounds very confusing, perhaps, when we just talk about it. So let's jump in and look at an illustration of this process now.
So here's a crude illustration, once again, that I've made on my iPad to illustrate how difference of means works in one-way ANOVAs. So suppose you're interested in measuring the battery life of 3 popular smartphone manufacturers. Here I've drawn Google in green, Samsung in red, and Apple in blue. And on the x-axis, we've got hours of battery life. So here I've drawn box plots showing that on average Google phones get 6 hours of battery life, Samsungs get 8 hours of battery life, and Apple iPhones get 7 hours of battery life. So the question would be, are these means really different? Is there really a significant difference between Google's mean, Samsung's mean, and Apple's mean? Well, that would depend a lot on how much variance there is in each one of those group categories. So here I've drawn the categories to be quite distinct, and you can see by, for instance, comparing Google to Samsung, that the Google user who gets the highest battery life of 7 hours is at the lowest end of the Samsung user. There you can see that the Google mean of 6 hours is very distinct from the mean of Samsung users at 8 hours. So we would probably expect to find in this kind of analysis that there would be a significant difference of means driven by, let's say, Google's difference and Samsung's difference. You can also see here that Apple users get on average the low end of a Samsung user gets at 7 hours of battery life. So once again, I think this figure illustrates that the means are quite distinct. So here I've redrawn just to illustrate sort of the contrast, the same mean averages for Google, Samsung, and Apple phones, but I've added a lot more variation to kind of how those averages are calculated. So here you can see that Google phones range from a low of 4 hours to a max of 8 hours. Samsung's range from a min of 5 hours to a max of 11 hours, and iPhones range from a min of 5 hours to 9 hours. So kind of the point here is that the variation within each group is a lot larger, which makes the difference of means a lot less pronounced, particularly when you see that the Google mean is well within sort of the bulk of observations of the Samsung mean. We thought about that as sort of these 68% or even 95% standard deviation. It wouldn't be statistically unlikely to get Google's mean from a Samsung distribution. Similarly, it might not be statistically unlikely to get an Apple mean from a Samsung distribution. So the idea here is that if the difference of means is really going to exist, then the variation between the groups has to be really bigger and a much bigger magnitude than the variation within each group, because of course when there's a lot of overlap in the timelines or battery life of each phone, we wouldn't really think that the difference would really exist except for through statistical sampling error. So let's look at how we actually conduct a difference of means test with multiple groups using a one-way ANOVA. So as usual, our null hypothesis is that the mean difference is 0. So if we have more than one group, we can say that the null hypothesis is x bar 1 is equal to x bar 2 is equal to x bar 3. And you can have as many groups as you want in a one-way ANOVA. So here I've just illustrated for 3 groups where, once again, all of the means for all 3 groups are exactly the same. Now, the alternative hypothesis for a one-way ANOVA is simply that the means are not the same, but this can actually manifest, at least with 3 groups, in one of 3 ways. So it could be the case that the mean of group 1 is not equal to the mean of group 2, although the mean of group 2 can be equal to the mean of group 3, or the mean of group 1 can be equal to the mean of group 2, and those cannot be equal to the mean of group 3, or the mean of group 1 is not equal to the mean of group 2, and the mean of group 2 is not equal to the mean of group 3. Any one of those is a possibility to satisfy the alternative hypothesis, although one of the limitations of one-way ANOVAs is you really can't parse out which mean is different based on the analysis and the results that you get. So one of those hypotheses is true if you get a confidence level enough to reject the null hypothesis, but you can't sort out from the one-way ANOVA which of those hypotheses in the alternate cases is actually going on with your data. So what we're going to conduct is called an Ftest, and an Ftest is done through an analysis of variance or a one-way ANOVA. And you can see that the word ANOVA is actually just kind of an acronym built from analysis of variance. So analysis of variance has two components. There is the sum of squares between groups, which we'll call SSB, and the sum of squares within groups, which we will call SSW. When you add the sum of squares between groups to the sum of squares within groups, you get the total sum of squares. Now, these concepts sound a little familiar, but we've kind of already seen them before. So we can think of sum of squares as really the difference of means between the groups. In this particular case, we'll be looking at how different the mean of each group is from the mean of all of the data or all of the groups. The sum of squares within groups, SSW, refers to how much variances there is within each of the groups. So if we have, let's say, group 1, how much variation exists just within that group, combined with how much variance exists within group 2, and how much variance exists within group 3. So if we add the sum of squares between groups, that is, if we add the variance between the groups that we've got to the variance that we have within each group, that gives us the total variation in our data, or what we call the total sum of squares. So let's look at the calculation of the sum of squares between groups first. As we kind of mentioned before, the sum of squares between groups is the difference between each group's mean and the mean of all of the data. Of course, we have to square those differences to get rid of the negative numbers, and we add them all together. What we're going to do then is we're going to multiply that sum of all of those numbers together by the number of observations per group. So let's look at an example with some made-up data. So I just made up some values that would correspond to the pictures we looked at earlier, where we have 3 cell phone manufacturers, Google, Samsung, and Apple, and we collected some data on battery life, such that Google's battery life on average is 6 hours, Samsung's battery life on average is 8 hours, and Apple's battery life on average is 7 hours. If we combine Google's data with Samsung's data and Apple's data, we get an average battery life for all cell phones of 7 hours. So plugging in for SSB, we've got Google's mean of 6 minus the total group mean of 7. We square that, plus Samsung's mean of 8 minus the overall group mean of 7. We square that, plus Apple's mean of 7 minus the overall group mean of 7. We square that, and then we multiply that sort of sum by 8, which is the number of observations we have per group. So we had 8 data points per group, and that's where the number n subscript groups comes from. So if we take 6 minus 7, we get negative 1. Square that, we get 1. Plus 8 minus 7 is 1 squared, which is 1. Plus 7 minus 7, which is 0, which gives us 0. That gives us 2 for our sum times our 8 observations per group, and that gives us a sum of squares between groups of 16. So once again, the idea here is that the variation between the groups, that is the variation between Google's phones, Samsung's phones, Apple's phones squared, is a total of 16. Alright, so now that we've calculated SSB, let's take a look at how we calculate SSW. Recall that SSW stands for the sum of squares within groups, which is a measure of all the variation there is within the categories. So for here, we're looking at cell phone manufacturers. SSW will be the amount of variation there is within each manufacturer's phone usage or battery life. So the way we calculate SSW is to take every observation and subtract the group mean from that observation and then square it so we get rid of the negative numbers. So here for this example, I've shown the formula. SSW is equal to the sum of group 1 observation I, so the first observation, minus the group mean squared, the second observation minus the group mean squared, and so on and so forth. So to illustrate how that happens, I've got a little snippet of data here from Excel. I've got my 3 phone manufacturers, Google, Samsung, and Apple, in column B. And I've got the mean listed at the bottom for each group. So Google phones have a mean of 6-hour battery life, Samsung has a mean of 8-hour battery life, and Apple has a mean of 7-hour battery life. So what I do then is I subtract the mean of each group from its observations. So for Google, the first phone has a battery life of 6 hours, so 6 minus 6 is 0. The second observation is 6, so 6 minus 6 is 0. 5.5 minus 6 is negative 0.5, and so on. I do that for Samsung phones, where I'm subtracting the Samsung mean of 8, and I do that for Apple phones, where I'm subtracting the Apple mean of 7. So once I have all my differences from the group mean, I'm going to square to get rid of the negative numbers. That's the final column of my Excel snippet. And then I can sum the square differences for each group. So the sum of square differences for the Google group is 3. The sum of square differences for the Samsung group is 3. And the sum of square differences from the Apple group is 5.5. I add 3 plus 3 plus 5.5, and that gives me 11.5, which is my sum of squares within groups. So in other words, I've got 11.5 squared units of variation within my groups, taking the observations and subtracting the group means from them. So now that we've calculated SSB and SSW, we can actually conduct a Ftest, which is going to be our test for statistical significance. But before we do that, just remember to keep in mind that now that we've calculated SSB to be 16 and SSW to be equal to 11.5, we can actually calculate the total sum of squares, or SST, by simply adding SSB and SSW together. So here we add the 16 for SSB plus the 11.5 for SSW, and that gives us a total sum of squares, or SST, of 27.5. Now that we've calculated SSB and SSW, we're almost ready to calculate the F statistic, which is our statistic we're going to use to test the null and alternative hypotheses. You'll note here that I've written that F is equal to the adjusted SSB divided by the adjusted SSW. Once again, the intuition is very similar to our one sample and our independent sample difference of means test, where we're comparing the variation between groups, which is on the top, against the variation within groups, which is on the bottom. Now, the big difference here, of course, is that whenever we calculate a statistic for sample data, we need to adjust the values in our formula by sample size. And that's essentially what we need to do here for both SSB and SSW. So once again, we're going to adjust them by the sample size using the following degrees of freedom. So to calculate the degrees of freedom for SSB, it is the number of groups minus 1. So in this case, we had 3 groups, Samsung, Google, and Apple. We subtract 1, and that gives us a degree of freedom for SSB of 2. For SSW, we're going to take the number of observations. In this case, each group had 8 observations for a total of 24 observations, and subtract the number of groups, which is 3. So our degrees of freedom for SSW is 24 minus 23 for 21. Then to adjust SSB and SSW, we're going to divide each number by its degree of freedom. So we're going to divide 16 by 2, and we're going to divide 11.5 by 21. That gives us a F statistic with the adjusted SSB of 8 divided by the adjusted SSW of 14.6. So our value of F is 14.6, and then we would need to consult with a F distribution table or a statistical program to determine whether or not a value of 14.6 is sufficiently past the critical value of F to reject the null hypothesis at a 95% confidence level. So here is an F distribution table with the critical values. You have to figure out the degrees of freedom in the numerator and degrees of freedom in the denominator. Use the table with the degrees of freedom in the numerator along the top columns and the degrees of freedom in the numerator along the sort of rows. And then it gives you your p-value, so you can pick out which value you specifically want for your critical value of F. So recall that for the numerator, for SSB, we had 2 degrees of freedom, so we're going to use the 2 column, and we had 21 degrees of freedom for the denominator. So here I've scrolled to the bottom of the table. We're going to use the 7 degrees of freedom since the table only goes to 7. And we're going to use that second column of values for 2 degrees of freedom in the numerator. Usually we're going to look at our 0.05 significance level. So matching up our 0.05 row with our second column, we have a critical value of 4.74. Since our value for our F statistic exceeds that critical value of 4.74, we would conclude here that we can confidently reject the null hypothesis at a 95% confidence level and conclude that the average battery life of the phones are different, although once again we can't really say which values are statistically significantly different from the others because F doesn't provide us that granular detail.